take a look at these three vectors. They are not just any vectors, but they are the column vectors of a matrix. Notice how the green and white vectors both lie on the same red plane. This red plane represents the span of these two vectors, the full range of directions that they can define together. Now, if we shift our focus to the purple plane, it's defined by the span of the white and blue vectors. Welcome back everyone. In our last video, we introduced column vectors and touched on the concept of the column space. Today, we are going to build on that foundation, diving deeper into what column spaces really mean. We will also explore the different possible column spaces for R3, our familiar XYZ volume. So let's get started. The column space C of A, this is column space is written as this, contains all vectors A times X. That is all combinations of columns. That's why I begin this lecture from this row interpretation and column interpretation. Because column interpretation says that A times vector X is nothing but a linear combination of all the column of A. That is a linear combination of column vectors. So column space is nothing but all the linear combination of the column vectors of matrix A. Okay, so this is column space. Now in this case, in the case of A1, all the linear combination of columns of A is nothing but R cube. So the column space of A1 is R cube. Whereas the entire 3D space. Whereas the linear combination of columns of A2 is not R cube. Because it is not filling the 3D space, but it is this plane, this YZ plane. So this YZ plane is the column space of R2, A2. All right. So we can say that column space of A1, the above matrix, is the entire R cube. All right. But the column space of A2 is the YZ plane. YZ plane. That is R2 because the plane is R2, right? So this YZ plane, uh, two-dimensional basically. Okay. Similarly, let us suppose we have this kind of matrix where you can say that where all the three columns are linearly dependent. Okay, so we can have this matrix A3. Okay, where the first column is 1 0 0. The second column is a multiple of the first column itself, 2 0 0, and the third column is also multiple of the first column, that is 3 0 0, right? So in this case, how it will look like? So this is the input vector space R3, right? So here the first column vector, this is A1. The second column vector is also here A2. This is x-axis. And the third column vector is also A3. So this entire line X is nothing but the column space of A3. Okay, so the column space of A3 is the x-axis itself, that is R1. That is a line passing through the origin. Also, see, always remember, because these are spaces, these are vector spaces, so they must pass through the origin because they should contain zero vector. So we have seen, see, this is passing from the origin, right? YZ plane. So this is a valid vector space. All right. Now we will dive deep into column space. I will show you some further visualization. Okay. Let us suppose we have this matrix. We have this matrix M 1 0 0 1 1 0 1 1 1. So first of all the three columns are linearly independent, right? So if we see this is the first column, that is the first column vector 1 0 0, right? This is the second column vector 1 1 0, right? This is the third column vector 1 1 1. All right. So let us suppose first we take the linear combination of these two vectors. That is the first two column vectors, v1 and v2. That is 1 0 0 and 1 1 0. So what is the span of these two column vectors? So it's pretty simple. Visually, you can see that the span is nothing but the xy plane, because both the vectors are lying in the xy plane, right? So this is the span of the first two columns, right? This is the span of the first two columns, right? Now we have this third vector which is lying outside the span of the first two columns. Okay. Now let us suppose I add the first column vector, that is 1 0 0, with this third column vector, that is 1 1 1. So I will get something like this, because I will simply move this orange vector at the tip of this vector, right? I can remove the orange vector for now. All right. So I will get something like this. Okay. So there is a plane passing through these two vectors, that is this green vector and this red vector. For now I can remove the second vector also, right? So what is that plane? That plane is nothing but this plane. You can see that this plane is containing both this green and red vector. Okay, so this plane is nothing but the linear combination of the first and third column vector, that is 1 0 0 and triple 1. That is 1 0 0. This is the first column vector and the third column vector 1 1. We have seen the span of first two column vector, that is 1 0 0 and 1 1 0. This is the span of the first two column vector, this xy plane, this plane. All right, we have seen this. Now this is the span of the first and third column vector, this plane, right? The first and third column vector. Now we will add, because we add one by one, right? We need to take the linear combinations, right? We need to take a linear combination of the column vectors, right? That is column 1 plus column 2 plus column 3, right? So I have added column 1 and column 3 first. Now column 1 and column 3 is giving me this plane. Now I will add column vector, sorry. Now I will add column vector 2, that is 1 1 0. So if I add column vector 2, that is 1 1 0, this vector will move, right? This red vector, this below vector will move at the tip of this. So this will be this. Okay. So now if you see now, see this second column vector, this has went outside the span. I will just remove this. This has went outside the span of the first and third column vector, right? This has went outside the span of the first and third column vector. So that's why these three column vectors are linearly independent, and they will fill the entire R cube, the entire 3D space, the entire R cube. All right, because their vector addition, their linear combination, column 1, column 2, column 3. This is the linear combination. We take we take the column 3, this green vector, then we add column 1 to it, that is the red vector, and then we add the second column vector, that is this purple vector. So this green vector is the third column vector, the red vector is the first column vector, and this plane is nothing but the linear combination or span of column vector 1 and column vector 3, and then we added to the linear combination to the linear combination of first and third vector, we added the second column vector, and it went outside the span. See, it went outside the plane. So if it is going outside the plane, then we can simply say that these three column vectors are linearly independent, and the linear combination will fill the entire 3D vector space. Okay, and you can also see if you take the two pair, the column vector 1 and column vector 2. If you take the column vector 1 and column vector 2, what you get this xy plane, this first plane. Okay, and if you take the linear combination of column vector 1 and 3, you get another plane. Now these two plane, the linear combination of the linear combination of two planes will give you this entire 3D space. The linear combination of these two plane will give you the entire 3D space. All right. So this is so also we are saying span everywhere. So the span of columns of A, independent or not, is column space. This is another definition. This is another definition. Important. the span of columns of A, irrespective they are independent or not, is column space. All right. So basically, column space is nothing but the linear combination of columns of matrix A. All the combination, all the linear combinations of columns of matrix A is column space. Or you can say the span of columns of matrix A is column space. Okay. So now we will see. Okay, we can also see one more example. Uh, this one. I have one more example for you. So let us suppose now we have the, let us suppose this is M1. Let us suppose this is M2, right? And this is nothing but 1 0 0 1 1 0. But the third one is nothing but the column 2 minus column 1. So this becomes 0 1 0. So we can simply see that here this column 3 is nothing but column 2 minus column 1, right? So in this case, the column 3 is a linear combination of the first two columns. So we can simply say that the column space of matrix M2 won't fill the entire 3D space, but it is going to be a plane, right? It is going to be a plane. Okay. So now we will see all column spaces of R cube, all possible column space of R cube, all possible column space of R cube. All right. So there are basically four possibility for column spaces of R cube, right? The first one, the whole space, the whole space R cube, the whole space R cube. In this case, the matrix A. In this case, matrix A has three independent columns. Okay, so we have seen this one, right? This M1, right? So this has three independent columns. This has three independent columns, and in this case, the column space, that is the linear combination of columns of matrix or the span of columns, is nothing but the entire R cube. So one of the possible column space of R cube is the whole R cube, right? And in such case, the matrix has three independent columns. We have seen this example also, this one, right? A1. This also, in this case also, the column space is nothing but the entire R cube. Okay. Also, this matrix 1 0 0 0 1 0, the identity matrix. Okay. This also has column space as R cube. That is the entire XYZ space, 3D space, XYZ 3D space, right? The second possibility for column space of R cube is a plane. A plane in R cube, but it should pass through origin, that is zero vector, right? Passing through zero vector, that is origin. And we have seen its example also, this M2, this M2, its column space is nothing but R2. Even this A2, its column space is nothing but R2. That is a plane passing through origin, right? So how a matrix will look like in this? So the matrix A has only two independent columns, only two independent columns. The third column is a linear combination of the remaining two. So one example, we have already seen two examples above. One example could be this 1 0 0 0 1 0, and the third entire column is 0. All right. So this is one such example. So in this case, column space of A is nothing but xy 2D plane, that is r cube r square. But see, this plane is still in r cube, right? Okay, this plane is still in r cube, but it is 2D plane, but it is still in r cube. So you cannot say that the plane is r square. All right. The third one, the third possibility is a line in r cube passing through the zero vector, that is origin. All right. We have seen its example also. This one A3, right? See, this is a line. This is R cube, input vector space is R cube, and this is the column space is nothing but a line passing through origin. All right. One another example. In this case, A has only one independent column. Only one independent column. Right. An example could be A is 1 0 0 0, and the remaining two columns are nothing but 0. So the column in space of A in this case is nothing but the x-axis, that is 1D. The fourth possibility, the fourth possibility is the single point 0 0 0, that is just zero vector in R cube. In this case, A is a matrix of all zero. A is a matrix of all zeros, right? That is A is nothing but 0 0 0 0 0 0 0 0 0. All right. So the column space of A is nothing but the single point zero vector, that is 0 0 0. So if we visualize this, all right. So this is we need to see all the possible column spaces of R cube, right? So first of all, we will draw R cube. This is R cube, right? This is R cube. So one possible such a space is the entire R cube, the first one, right? The another one is a plane passing through origin, is a plane passing through origin. Okay, this is a plane in R cube. This is a plane in R cube passing from zero vector, that is origin. This is one case, and this is the second case. The third one is a line. So maybe just this entire line. Uh, hello. Maybe this entire line passing through origin. Okay, so a line, just give me a minute. Okay, a line in R cube passing from zero vector. The fourth case is nothing but this zero vector itself, that is the single point zero vector. And the first case we already discussed. The first case is this entire R4. Okay. So these are the these are the only four possible column spaces of R cube. Remember this. These are the only four possible. That is the whole space R cube. a plane in RQ passing through origin, a line in RQ passing through origin, and the origin, the single point itself. And these are its example matrix representations. Okay. Also, one more thing. This is one more important thing is columns of matrix is not column space. If you are saying this that columns of matrix is column space, no, you are totally wrong. It's the linear combination of columns or the span of columns is column space. Okay, so this is this point is very important that uh, columns of matrix is not column space, is not column space, but the linear combination or span of columns is column space. All right, and column space is a subspace. Okay, column space is a subspace. Okay, you have the input vector space R cube. Here, there are four possible subspaces. The entire R cube, a plane passing through origin in R cube, that is a column space, which is a subspace. A line in R cube passing through origin, that is a column space, which is nothing but a subspace. And the single point, the zero vector, that is also a column space, and which is a subspace, right? So column space are nothing but subspaces. All right. So I think that's all for today. We have covered a lot of things. Column space, I think column space is totally clear to you now. We have seen some nice visualization, okay, regarding column spaces, especially this one. This visualization is really important. Okay, so that's all for today. I think the main crux of the video is that column space is nothing but the linear combination of columns of matrix or span of columns. That's all. Nothing else, nothing complicated. Okay, so thank you for watching my videos. So if you find these videos really helpful, then do like the videos, subscribe my channel, share my videos and share my channel with your friends, with your colleagues, with your GATE aspirants, or any machine learning engineer or researcher. Okay, so thank you. Uh, See you next time. Till then, bye.